So today really what I want to talk about is technology development and product engineering. But first of all, maybe a little bit of a background. I'm an engineer. Yeah, see, my wife's right. That was a quick social experiment. She says, that's a conversation killer every time you say that. So thank you very much for, now I have to go home and tell her she's right. That just doesn't always work. So I'm now early in my fourth decade of being an engineer, which is kind of shocking. When I did the math this morning, I was a little surprised about that. Both being an engineer itself and an academic and teaching design process from an engineering context. But I also have a degree in psychology, and that was actually my first degree in college. So I come at it from a little bit different perspective, right? Because innovation and new creativity really seems to happen at the borders of disciplines. And so actually, I was multidisciplinary before it was even fashionable. You know, I was just a young kid who couldn't figure out what he wanted to do at 20 years old, right? Like so many of us at that particular time. But nowadays, multidisciplinary, the phrase is really becoming, how about antidisciplinary? Take the blinders off to the way you normally think and focus with an open mindset. And I like to take it a step further than that. It's not just psychology or engineering or chemistry or physics or history, linguistics, whatever your field is. But it's really, at the very basics, about combining art, design, science, and engineering. If you lay them out on a quadrant, you know, art is kind of creation of beauty, or put in your own word there for beauty, but it's really about creation of something. And design tends to focus on the application of the beauty, the application of emotion. Science, the creation of knowledge, the fundamental understanding of things, the core physics, chemistry, math, biology that we all use in our daily lives to develop our engineering tools and apply that knowledge and science. So I am an engineer, and I like to work with my colleagues, both my professional colleagues and my students, to make things, very complicated things that have a lot of mechanical engineering and electronics engineering, things with very significant engineering challenges. And over the years, we've become pretty good and had the good fortune to work with on a number of interesting projects here in a number of interesting fields. And we've had the good fortune to work with a lot of companies, both big and small. And what I'm going to talk to you about today is the process of how we've come to codify this process that has allowed us to do so many of these things that we've shown up here. But let's take a step backwards for a moment. And I want to talk to you about a brief history of making, okay? I'm sure everybody's heard about the maker movement now. Everybody's making things again. But let's take a step back, say maybe to the start of this country. And if we do that and look at yesterday, we realize that a lot of the people that founded this country were makers. Not because they wanted to be, but because they had to be. They designed and made their own houses. There was a coupling between design and making. So they'd make their own houses, perhaps make their own thread for their own clothes, maybe make their own shoes, or shoes for those around us. But maybe they didn't always do that themselves, but most people were makers. If we suddenly jump to the 1920s, start of the Industrial Revolution in the US anyway, in that era, right, people stopped making final products. They made parts of products, right? They made thread. They made cars on assembly lines. And so what ended up happening was that we had the separation at the start of the industrial age of design and build. If we fast forward to the early 2000s, I was involved in a project at MIT where we reimagined engineering education in the aerospace department. And we went from a core engineering curriculum to a curriculum based on conceive, design, implement, and operate systems. And the reason for that is because the people out there in the world told us, as engineering educators, that yeah, MIT is great at teaching math and science, but these kids cannot build, these kids cannot put systems together, these kids cannot communicate, and they can't get their ideas across. It's a little bit of an exaggeration. Obviously they can, because they're really smart kids, right? But the purpose is, we really wanted to get those things together. So let's go from yesterday to today. Over that time between the start of the Industrial Revolution and today, we basically democratized consumption, right? We figured out how to make a whole lot of stuff that a whole lot of people can have, at least in the first world. We are in a society now that really lets everyone make everything else for us, in general. I mean, obviously, maybe we knit or whatever to make things for our friends, but as far as the things that we live with, essential on a daily process, other people make for us, even our morning coffee. So now, let's jump to the future. What is today coming in tomorrow? So I talked about the maker movement, and it really is fueled by a passion of makers. But it's also fueled by technology. So what that's going to engage with is we're going to democratize production now. So the maker movement is coming out, and what's enabling that is not only people being interested in making things and getting their hands on, but there's industries that have grown up around helping people make things. So for example, computer-aided software, originally designed around designing automobiles and rocket ships and things like that, okay, but it's now come down with the advent of faster processing power and, quite frankly, more computing power in your smartphone than what was ever on any of the big spaceships in the 1960s, has now made this stuff available to the average maker. Anybody can design things now in software. We now have desktop 3D printers, so we can print the things that we imagine now as makers. And if we want to do hard technical things, we now have places we can start to go to build things and use tools. Okay, this is a place called Artists Asylum in Somerville, a suburb of Boston. Somebody knows it out there. That's good. But there's a lot of other places like this out there where basically you can go in for a fee and learn to use tools and things like that you want to do. So let's talk about what's going to happen tomorrow. I mean, not in a figurative sense, but certainly within the next few years, right? We see the rapid pace of technology evolution going on around us all the time. Well, as I was preparing for my talk, I happened to trip across this. This was just published a couple of weeks ago. And it's Gartner's top 10 list of trends for 2015. Computing is everywhere. Pervasive computing, they talk about. Okay, so that means everything in it's going to have a little bitty smart chip in it, and it's going to know something, and it's going to be able to do something. The Internet of Things. I don't know if you've heard that expression before, but basically it means that every physical device in the world is going to talk to the Internet and talk to each other, right? Your refrigerator's going to call you at work and say, hey, you left the door open, you idiot. Stop doing that. I'm not sure if that's a good thing or a bad thing, but nonetheless it's happening. 3D printing, we already talked about a bit. It's becoming to the desktop, becoming more pervasive, available for other people. Advanced, pervasive, and invisible analytics. Things are going to be smart, being able to figure out what's going on. Context-rich systems, cloud client computing, and all the way down there, more and more technology. So if you want to play in this space, you're going to need a few things. Facilities, components, funding, and process. Well, the facilities are all on the way. We talked about the makerspace already, the Artist Asylum, but there's another place out there called Tech Shops now that's starting chains around the country that's pretty interesting because they put millions of dollars of machine equipment and things like this into a space that you can go in and pay, I don't know, a few $100s a month or whatever it is to go join this place, and you can work a lathe, you can solder things together, you can build things, you can 3D print, whatever you want to make. So these kind of places now give you the ability that not so long ago was only available to people in big engineering firms or big automotive firms or places like that, serious hobbyists. And so the world is now at your doorstep. The other thing that's interesting is because of faster computing power, smartphones and other things, the components are becoming rapidly available. And at a cost point that 10 years ago, or an availability that 10 years ago didn't exist. So if you want a wireless chip now, you go to a website like DigiKey and put in wireless chips or any other place, and you can decide, well, do you want Wi-Fi? Do you want 3G? Do you want 4G? What do you want? You just order the thing. That, believe it or not, was not true 10 years ago. These things did not just appear. This is all new technology. Microsensors, accelerometers, 3D motion sensors, GPS, all of those things have been enabled by the mass production of smartphones that have all these little sensors in them at a volume that make them now price available to put in all these other devices that you may want that kind of information in. The other interesting thing that's happened is funding. Used to be the old model is if you wanted to start a tech company, you got an idea, you maybe went in your garage and built something, and then you went around and you talked to your friends and family and you got your first round of funding, right? The friends, family, and fools, right? Round. So you got a little bit of money there, right? Got your first prototype off the ground, then you went to the angels, and then if you were really good and you really needed a lot of money, then you'd go up to venture capital and go on and on and on. A pretty laborious process, and boy, that's a lot of filters to go through. But nowadays, we have crowdsourcing. We can crowdsource money for our ideas. And not only do we get money, but we also get a really early feedback on what the market looks like. Is the market going to accept this? And these are a couple of projects we've had the chance to work on. I'm just throwing up there as an example. Little home security system from a company in New York City. Initial crowdfunding request, $100,000, $1.9 million raised. A personal robot called Jibo, spin out of the MIT Media Lab. We had a chance to work on that as well and develop some of the early prototypes for that as well. Similar story. Small fundraise initially expected, but boy, did it take home. People really want the thing. Now they've got the money to build these things. And makers are able to play in that space too. So makers are able to go in and raise funding to make things for more makers. So Formlabs is a popular one right now as well. But what's most important, and what I like to think the most about now, that we've set up this whole ecosystem for new things to be made. It's the process by which things get made. And it's this process that over the years that, we've seen in textbooks and we've taught in courses and we've applied in our daily lives in the engineering world. We still see some people running into some hurdles with some things, and so we've attempted to put more process around it, and we think we've come up with something that works pretty well. That's this chart. On your left, the horizontal axis is effectively time. The vertical axis is essentially risk. We're not really dimensionalizing anything, but it gives you an idea of what it looks like. In the early stages, if you're going to develop a project, you really have to answer two questions. One is, can I make it? Is it technically feasible to build it? And the second case is, if I build it, is anybody really going to care? Does there a business viability around this to have a successful project? And as you go through the stages of the process, you want to reduce that risk until when you're finally in manufacturing, you've got the home run. So over here on the left side, we have the role of research and the research of academics and understanding how people behave. Fascinating to understand those things and think about that in the context of how you might make and develop products and tools around that. The application of physical knowledge, core math, science, and physics. Then we go into a phase called technology development. I'm going to skip that for a moment because I'm going to dive into that in a lot of great detail here. And then we go into the more commercial world of design and support on the business side and manufacturing. In the research phase, we're asking a lot of hard questions, right? Can we do it? Should we do it? How can we do it? And how should we do it? So in this technology development space, even the National Science Foundation a few years ago realized, why is it so hard to get good ideas out of all these universities and all these research labs and commercialize them into products? And a part of the problem is because that gulf between research and product engineering, this technology development, is so hard and so risky. Mr. Adolph from Booz Allen quoted it and said, how do you know when you're doing technology development? It's when your boss comes in and says, what are you working on? And you say, I don't know, but I think it's going to be real cool. And the boss says, well, when am I going to get something out of this? When are we going to get a return? You're square in the middle of technology development in that space. They call that the valley of death. It's a highly risky area where a lot of good ideas come and die, because they can't get to the other side. Maybe they should die or maybe they shouldn't, but the process can help those that are worthwhile make it. The other side, maybe perhaps a more positive view, is the Darwinian sea approach. All these good ideas go in there and meddle around and get connected together until finally something really good comes out the other end and comes crawling up the other side and becomes an innovation or a new business. So what I want to do is I want to walk through a case study. It's a product called PowerTap. It's a sports technology product. A lot of good friends and colleagues have been involved with this project. And PowerTap is a product that came out in about 2000. And it measured power output for cyclists. It was a hub that was built into a bike wheel for a racing bike or a triathlon bike, and it would tell you how much power you're putting out at any one point in time, just like horsepower in a car or watts of power output. I want to walk you through the technology development piece in a lot of great detail and then talk about the product design piece as well, because I think it's interesting to understand and compare and contrast. Technology development really is about what I would call applied research and imagination. And what goes on in that phase? And the first thing you'll note here is that there's no implied timeline, there's no implied order here, historically, and that's important because they shouldn't be. Kind of everything has to be going on at the same time, and everything has to advance a little bit at a time from all these different aspects of it I'm going to talk about in order for the things to come together properly. The first point was there was a bunch of scientific research out there that people in sports physiology had done that said if you use power output to monitor your training and train by power output. As a cyclist, you will improve quicker than any other method, including time-based training, heart rate, whatever else was out there. So you can see the value of that. If you're a cyclist, what do you want to do? If you're going to go out and train, you want to train and get quicker. So based with that scientific knowledge, let's explore the intellectual property space a little bit. What other products are out there? Do we have room to actually bring a product to market? Can we get our own IP if we think that's important as a business decision to have IP around what we're doing? So that's part of it. And there's developing prototypes. So the way we like to do technology development is somebody comes to us with a technology problem. What we do is we assess the whole system that they're trying to get through, what it is they're trying to get out the other side. And we say, okay, what are the key technology hurdles we're trying to overcome? And we build little breadboard prototypes for each one of those little hurdles, maybe totally disconnected from the whole system, to view if we can prove that we can solve that problem. In this particular case, at that particular time in technology, the hardest problem to solve was wireless communications. We didn't have chips yet that you could just go buy. So this little proof of technology prototype, which obviously doesn't look anything like a bike wheel, was used to prove out that you could, in fact, strain a strain gauge, which is what measures power, essentially in the final product, and get that information off of the device that strained the strain gauge onto something else across the room, which would be up on the handlebars, and then provide that input to the cyclist. So we've proved out the technology hurdles, and then also, of course, user research. An interesting aside here, but I think it's a really important aside, and that's the whole field of user research. And this is when I kind of put my psychology hat on here for a little bit. There's this hierarchy of needs that people have. The most explicit ones are the ones you can say or think. You know, like this morning at the hotel, I got into the shower. I'm trying to turn the darn shower on, and I realized that the handle is backward. It doesn't go the way that it should. It's, you know, not lefty-loosey, righty-tighty. It's the other way around. Who the heck thought of that, okay? So that's something I can say, right? And I can think, this is not right. So that one's pretty explicit. That one's pretty easy to solve. If that shower in my house or in the gym or wherever I frequent, I would expect in 3 or 4 months, I'd kind of probably forget about it and just be on autopilot. And I'd go in there and I'd struggle with it a little bit every day and not even think about it, but yet eventually end up figuring out how to turn the water on and take a shower. But if somebody from the outside were to observe what I was doing, they'd come in and say, oh, look, there's a struggle this person's having in their life that we can solve. So that's the observed ones. Sometimes there's the knowing and the feeling and the tacit ones, and then there's other times there's these latent needs, things that people can dream about, right? That you don't even know you have, right? I bet nobody in this room 15 years ago knew they needed to have a smartphone. I mean, somebody had to imagine that, right? And so what you get is, on the explicit sides, it's low innovation. It's about product delivery. It's like, okay, next season we'll make it in blue because that's the color season of the way. Okay, nothing wrong with that. That's great. We have to do those kind of things. But it's not a high innovation like you get on the other end of the product, which can really result in a surprising, delightful experience. And my favorite quote for this process comes from Mr. Henry Ford here, who said, if I'd asked my customers what they'd wanted, they'd have said a faster horse. Hopping back to what we were talking about, we went out to the user research and we asked the people, we asked cyclists, we said, do you want a power measuring system for your bike? I said, what the heck for? No. You know, I already spent enough on this bike. I don't want to spend another, $700 on this thing. And then you hand them the scientific research, or a training book actually that was based on the scientific research. Boy, 3 days later you get a phone call from them and said, when's it going to be ready? So the lesson there is, you have to be able to understand enough and mix all these things up and understand what's going on to be able to define whether or not you've got the market for this type of thing. And the other thing, of course, the business viability. You need a business plan to make these things happen, right? So in this particular case, a lot of people, when they were informed about what Toon Corporation was doing, they'd say, why don't you do this for rowing, right? It's a really good thing. Quite the fact of the matter is there was, at the time, barely a market for cycling. That was prior to the big cycling boom in the U.S. There certainly wasn't a market size for rowing to make it a viable system. What's happened now, if we look at our chart, is we've taken now an invention and we've added some insight into the market. And through that technology development piece, we come out the other end of the technology development phase with an innovation. We've got a business case, we've got a product plan, now we have to design it and build it. This part is very linear, and it goes pretty smoothly as long as you stay on this process. But the first phase is working with the concept and figuring out what the concept is and defining the basic system architecture. In this case, we say this is a looks-like system. So you can see here in the very first stage, we took the proof of technology bit, made it round so it would go on a hub that can be built into a bike so you could actually ride the thing outside and collect the data. The next phase that happens is what we call the alpha prototype. Really focus on the hidden technical details of the system, and this becomes the works-like, looks-like prototype. So it's going to work exactly like the final product. It's going to be able to collect data like the final product. It may not last as long because we haven't gotten that far yet, but it's going to work like it and it's going to look like it. So you can get both feedback from users and feedback from particular customers on what they think of the product and also how it works. And once you've got through that phase, then really focus on what we call the beta prototype of works like, looks like, made like. And that's a lot of what we call in the engineering world DFX, or design for whatever. Okay, design for manufacturing, certainly, because you have to build it. But depending on what you're building and what you're developing, there may be other important factors. It could be designed for sustainability, could be designed for scale, whatever those issues are. But that's what happens in this phase. And then finally, you go into the pilot production, and then it's works like, looks like, made like, and is processed like. So these are the first ones coming off the assembly line. Now that's when you drive the final risk out of the system on the manufacturing side. The way I like to look at this in another format is the technology development really is about identification, characterization, and integration of technical, business, and user factors. So we start the technical development piece, technology development piece, which is kind of a foggy idea of where we're headed. And so we go out and collect little bits of knowledge here and there. And you can imagine things in the Darwinian sea, little cells or little antibodies that are looking to combine themselves in a unique and useful new way that we can come with a product out the other side. Product development then is really figuring out how do you make a lot of those, right? In a scalable way that's going to be manufacturable and can be delivered. In summary about these two concepts then, technology development really is about prototyping to come up with your requirements. Product development or product engineering is the requirements drive what the prototypes are. If it has to be a certain weight, has to have certain tolerances, that's what drives your prototypes at that stage. As I mentioned earlier, technology development is very, very risky. There's a high probability of failure in that area. But that should be accepted because the outcomes are what you're after. You want the successes. We had a client at one point, Motorola, and they had an internal team. It was a technology development team. And we asked them, I said, well, how do you measure success? And he says, I figure if we're not failing on our projects 50% of the time, we're not in the right spot. He says, more than 50%, we're doing research, and that's not our mission. Less than 50%, we're not pushing our boundaries. And obviously, for every organization, it's different what that number ought to be. Once you get into product engineering and product design, failure really should be unconscionable. You should have anticipated the hurdles and should have already proven those out before you move into that stage. Technology development can be highly divergent. You're looking for new ideas, looking for new ways to do things. Where product design, of course, is highly convergent. It's entrepreneurial. As I mentioned, product engineering is very process-oriented. But the magic bullet in all this is realizing that the difference between technology development and product engineering, although it's engineers doing both, are as different from one another as flying an airplane and playing basketball. Some people may be really good at flying airplanes or playing basketball or both, and you have to realize that some people are not either genetically suited or predispositioned or educated or socialized to playing basketball or flying airplanes. But maybe some people can do both. But you certainly should never play basketball and fly an airplane at the same time. All right? And often that's what we find is that people start into technology development and get in there and they grab the first good idea that comes along and says, let's go. Wrong answer. Take time for the divergence, figure out which ones are going to come through, and let the best answers float to the top to be selected to go through. So don't rush forward until you've put the time and the effort into it. And this works for sports equipment, low-water version toilet flushers, decorative lights in the city of Houston that are controlled to match the phase of the moon, electronics for your house. You can find these at Lowe's or Home Depot or wherever, right? The little pop-out outlets. Interesting little innovation here. There's 3 outlets in the space for the wall socket. In the standard US wall socket, there's a space of 3 outlets from where normally you can fit 2. The best way we figure out how to make that happen was the spring mechanism that causes it to pop in and out are also the electrical systems. Dual use of technology. And also works equally well in laboratory test equipment designed for the medical industry. The process is the same. It doesn't matter what it is. If it's got complicated mechanical electronics involved, take the time, do the technology development, and focus through the steps, and there's a good chance you'll be successful. The infrastructure has been built around us now for all of us to have a chance to play in this space if we're interested. So if we understand the process and understand where we are on the map, there's a good chance we can be successful. And the last thing I'd like to do is just acknowledge my current team that I'm working with. It's just a fabulous group of people that allow us to be able to create these new things and work in this environment. Thank you very much.